Hello chemists, this is Miss Placino and you are watching Screencast 6.5 on limiting reactants. Today what we're going to talk about is what's going to happen in a chemical equation when the reactants are not in equal stoichiometric amounts. In other words, what are the consequences when we don't have enough of each reactant so that the reaction goes to 100% completion and all of the reactants are converted into products. Initially, this might sound kind of complicated and difficult to figure out, but in reality, you run into limiting reactant type problems on a very regular basis. To show you what I mean, let's take a look at the do now. You decide to throw a pizza party. Each guest receives 2 slices of pizza and a can of soda. If you have 3 pizzas, each with 8 slices, and 100 sodas, how many people can attend the party? Let's start by trying to take this out of English and translate it into a chemical equation. We've got 2 slices of pizza, draw pizza, put some pepperoni on it, plus a can of soda. Going to make a party guest. All right, so we're in a 2 slices to 1 can makes 1 guest ratio. And we know from the previous lesson that ratios are going to be really important when doing any sort of stoichiometric problem. So I have 3 times 8 or 24 slices. No math to do with the cans. I have 100 cans of soda, and I'm trying to figure out how many people in total can attend the party. Hopefully before you even do any math, you can come to the conclusion pretty quickly that you really overdid it on the soda. You've got way more soda than you can possibly hope to consume if you keep this 2 to 1 to 1 ratio consistent. Based on what I've got, 24 divided by 2, or if I want to make this, turn this 2 into a 24, if I have 24 slices, I would need 12 cans of soda for a total of 12 people. Oh my goodness, such a mess. P-E-O-P-L-E. There we go. So it doesn't really matter that I've got all of this extra soda. It's not really impacting how many people can be invited to my party. If I had to determine which was the limiting reactant, even really without talking about the terminology specifically, hopefully you come to the idea that it must be the pizza, because the pizza limits the number of people I can invite to my party. That's the right way to think about a limiting reactant problem. You really need to look at the 2 reactants and figure out which one gives you less. If it was the soda, I can invite 100 people to the party, and I definitely do not have the pizza to cover such a lengthy guest list. So let's get into today's lesson, and we'll start off with some terminology. We've got the limiting reactant, and that's the reactant that's going to run out first in a reaction. It's going to limit the amount of product formed. We'll have an excess reactant. As the name suggests, that reactant is present in excess. It's going to be left over at the completion of the reaction. So to get back to our pizza and soda example, pizza is our limiting reactant. It runs out first and it limits the number of people we can invite. Soda is the excess reactant. At the end of your party, you're going to have 88 cans of soda left over. Whole process that we're going to go through for these types of problems is to try to determine how much product would be formed from each of the reactants. Whichever reactant produces a smaller amount is deemed the limiting reactant, and then we really use that one to figure out the rest of the calculations. So this is going to be very, very similar to what we did in the previous lesson with ideal stoichiometric calculations, just with one additional step, trying to figure out the limiting reactant. Before we get into an actual chemical equation, let's look at another example. Let's say you're building tricycles again, and we simplified the process down to wheels and pedals. Generally, when talking about limiting reactant problems at this point in chemistry, we're just going to give you 2 reactants. Giving you more than 2 is definitely possible to work with, but it's really just going to make things more complicated, and we don't need to do that to you just yet. So if we started off with 10 wheels and 4 pedals, we can make a total of 2 tricycles. Wheels react with pedals to form tricycles in a 3 to 2 to 1 ratio. If I have if I've got 10 wheels, that means that I can basically make 3 bikes with 1 wheel left over. If I've got 4 pedals, I can make 2 tricycles, nothing else left over. So I'd say that pedals is my limiting reactant because it dictates how many tricycles can be made. Therefore, wheels are the excess reactant. I made 2 tricycles, like if I change this to a 2, that means I have to double everything else. So I must have used 6 wheels, and if I started with 10, that means 4 of them are left over. Let's change the ratio a little bit. Let's say we go to 15 wheels and 12 pedals. What's going to happen? With 15 wheels, 3 of them are required per tricycle. I can make a total of 5 tricycles. 12 pedals to work with. I know only 2 are required. 12 divided by 2. I could have 6 tricycles made. So it looks like wheels are going to be my limiting reactant. I'm only going to make 5 tricycles. Wheels are limiting. Pedals are in excess. If I make 5 tricycles, I've got 5 times 2, or 10 pedals used. 12 minus 10 gives me 2 pedals remaining. If I start off with equal amounts, 12 divided by 3 is 4, 12 divided by 2 is 6. So again, wheels are going to be the limiting reactant. I can make 4 tricycles. Wheels are limiting, pedals are in excess. If I make 4 tricycles, 4 times 2 gives me 8. 8 subtracted from 12 gives me a total of 4 pedals remaining. Figuring out limiting reactants in a chemical equation is going to be relatively similar to what we're doing here. You need to figure out how much of your product can be made. Granted, it's going to be a little bit more complicated when we're talking about a chemical equation than with tricycles. Figure out which one is limiting, which one is excess, and ultimately how much of your product you can make and how much of the other reactant will remain left over. So let's look at some practice problems. Let's say you've got this equation, nitrogen reacting with hydrogen to form ammonia, and we've given you information about the mass of each reactant, and this is what we're going to call our actual yield. You go ahead and you run this reaction using 16 grams of nitrogen, 6.2 grams of hydrogen, and you recover, or you produce 10.1 grams of ammonia. Now, the first question you're going to have to contend with is which reactant is limiting. And in your workbook, put a star next to this. This is a time-consuming step and arguably the most important part of a limiting reactant problem. So let's get into it. You've got an unbalanced chemical equation. Let's take care of that. 1, 3, and 2. Okay. In order to figure out which reactant is limiting, we have to figure out how many moles of ammonia, NH3, can be produced using 16.0 grams of nitrogen and 6.2 grams of hydrogen. So I'm going to start with N2, and I like to identify which reactant I'm working with just to help me keep my work organized. I'm going to start off with 16 grams. We'll put that over 1 to keep things neat. I know that I'm looking to get out of grams of nitrogen and into moles, and I know that 1 mole of N2 is equal to about 28.0 grams of nitrogen. Grams cancels out, leaves me with moles of N2. I am not interested in N2, I'm interested in my product, in this case NH3. From the balanced chemical equation and stuff we talked about in the previous lesson, I know for every 1 mole of N2, 2 moles of NH3 can be produced. And I can actually stop right here because I've got moles of NH3. I could take it a step further and convert into grams if I'd like to, but this is good enough. I'm into some quantity of my product. So I can go through and perform my math. And if I start off with 16 grams of nitrogen, I can hope to produce 1.14 moles of NH3, assuming all 16 grams of the nitrogen react. I'm going to repeat the same exact process for H2. I can get into moles of H2 by taking, 6.2 grams. I know that every mole of H2 has a molar mass of 2 grams, and I can use the balanced chemical equation to see that 3 moles of H2 are required to produce 2 moles of NH3 just by using the coefficients. Moles of H2 cancels out, grams cancel out, and I'm left with moles of NH3. When I perform this calculation, I can see that with 6.2 grams of hydrogen, I'm able to produce 2.1 moles of NH3. So this question is asking me which is the limiting reagent, and I'm going to pick the one that produces the smaller amount of ammonia. So N2 is my limiting reactant. And a lot of times you'll just see LTD for limited. It's present in a limited supply. That means any other question that asks me about how much product is going to be produced, I can basically ignore the 6.2 grams of hydrogen. It's present in excess. The nitrogen is going to run out first and limit the amount of product produced. So this is the most involved step because you have to compare both of your reactants. Once you know the limiting reactant, you're kind of on the fast track to getting this all figured out. The next question that tends to come up is what mass of product can be produced. So here we're looking for the mass of NH3. I could ask you about how many liters, what is the volume that can be produced, but it's really the same procedure. I already figured out that nitrogen is my limiting reactant and that I should be able to produce from my 16 grams of nitrogen 1.14 moles of NH3. I'm looking for a mass in grams. So hopefully we recognize that this is just a straightforward mole conversion using molar mass. 1 mole of NH3 has a molar mass of approximately 17.0 grams. They'll cancel out, and I'm going to do the math, and I'll see that I should make 19.4 grams of NH3. Oh, tells me up here I didn't make that. I only recovered 10.1 grams. Don't stress, we'll get to what that's all about in just another minute. Another question that you tend to get asked is what mass of the excess reactant will remain? We know that nitrogen is the limited, hydrogen is present in excess. We're trying to figure out, once all the nitrogen has been used up, how much hydrogen, in terms of grams, are going to be left over at the end of the reaction. So we can't really compare these directly. Hydrogen and nitrogen have two very different molar masses, so we can't just figure out using the masses provided in the question. We need to ultimately get to moles, figure out how many moles of hydrogen were used, convert that into grams, and subtract. So I know that I started with my limiting reactant, 16 grams of N2. I need to talk about that in terms of moles. So I have 28.0 grams of N2 equals a mole of N2. I'm interested in just talking about hydrogen, not nitrogen, so I need to use my mole ratio. For every 1 mole of N2, it requires 3 moles of H2 to completely react. N2 is gone. And now I need to get into grams, so for every 1 mole of H2, that has a molar mass of 2 grams. So now I'm out of moles into grams, and I can calculate that 3.43 grams of H2 was used. I know that I started off with 6.2 grams, so I can do 6.2 minus 3.43 grams, and that's going to tell me what mass is left over. So I calculate 2.77 grams. I got to be careful about sig figs. I can only have one significant figure after. So let's call this the 2.8 grams of hydrogen is going to remain. This is the key step that most students forget about when they're first doing limiting reactant stuff. Remember, you're initially calculating the grams of H2 used, not how many are remaining. In order to figure that out, you need to subtract what was used from what you started with to figure out what remains. The final question that you tend to be asked is, what is the percent yield of the reaction? And in order to talk about, or in order to calculate this, you need to know a formula. The percent yield formula is simply this. It's the actual yield divided by the theoretical yield times 100. And percent yield provides a meaningful way for us to evaluate how effective a reaction was. So if you'll remember, we had 10.1 grams as our actual yield, and we had 19.4 grams as our theoretical yield. If you're wondering where these numbers have come from, theoretical yield is calculated. Basically, when you go through and you figure out how much product could be produced based on the amount of limiting reactant that you start with, you are calculating the theoretical yield. This means everything goes 100% correctly and all of your limiting reactant gets converted into product. In reality, that doesn't always happen. This is where your actual yield comes into play. The actual yield is when you go into the lab, you start off with the masses of each reactant that's provided in the question, and you run the reaction and you measure what you get. It's not always going to be the same, and in fact, in most cases, you end up making less than you expected. And there are a variety of reasons for that. You can sometimes just not get the reactants to convert into products. You might be producing other products that you did not intend to, that were unwanted. So those are two typical reasons why your percent yield is usually below 100%. So let's get back to that question. What is the percent yield of the reaction? Well, we know that percent yield is equal to actual divided by theoretical times 100. Make sure you're showing me that formula when you go to solve these problems. The actual yield is provided in parentheses. It's 10.1 grams. You calculated that you should be able to make 19.4 grams. Multiply that by 100, as that is the definition of percent. And you should come up with approximately 52.1% yield. Not great, but probably pretty realistic. Okay, those are the 4 steps that you really need to be able to walk through. And in your workbook, you've got, I think, 4 or 5 different practice problems to work with. First and foremost, you need to figure out which reactant is limiting. That's done really just by going through and performing calculations to figure out how many moles of the product in question can be made. You can actually kind of streamline the process a little bit, maybe go directly to grams. That way you don't have to really take care of step 2. Once you know the mass in grams of the product that's produced, you're able to calculate the percent yield. You know that you're calculating the theoretical yield and providing you with the information on the actual yield, and then it's just a simple application of the formula. And the only other thing that you might be asked to calculate is what mass of the excess reactant will remain. Remember, when you go through and initially perform that calculation using the limiting reactant, you are figuring out how much of the excess reactant was used. The question asks you how much remains. You need to take the original mass that you started with, subtract out the mass that was used to figure out what is left over. This is overall, not a super involved process, but it does require you to work methodically, work stepwise, and really show what you're doing. Don't get lazy with things like units and including what substance you're talking about. It's really worth taking the extra couple seconds and writing down the formula of the substance you're working with. It'll save you a lot of headache down the road. All right, thank you for tuning in, and I hope you found this screencast helpful.